So in section 9.3, we started looking at series and trying to determine whether they converged or not, and we even added a few tests or a few different ways to tell. In this video for section 9.4, we're going to add a few more ways to determine if a series converges or not. And the first one is a comparison test, which is a fairly straightforward and easy one to use. It's just saying, suppose the terms that are in the a sub n series and the terms that are in the b sub n series are both positive, and a sub n is less than b sub n for all n beyond any value that we want to choose. So at some point, b sub n overtakes a sub n. So if the larger series, b sub n, converges, then obviously the smaller series, a sub n, must also converge. And if the smaller series, a sub n, diverges, then the larger series, b sub n, must also diverge. So if we want to determine does 1 to infinity of 1 over n squared plus 2 converge or diverge, we can actually compare that to a p series. So here's what we're going to do. Since 1 over n squared has to be greater than 1 over n squared plus 2. Right? 1 over n squared would be greater than 1 over n squared plus 2 because if you're adding 2 in the denominator, you're technically going to have a smaller number because you're dividing by a larger number. Since 1 over n squared is greater than 1 over n squared plus 2, and we know the series from n equals 1 to infinity of 1 over n squared converges. How do I know that? I know that because it's a p series and p is greater than 1. So 1 over n squared converges. Thus, the series from n equals 1 to infinity of 1 over n squared plus 2 converges also. So let's look at a slightly different one that's going to require just a little bit more thought. So we know n is going to infinity. So at a certain point, this negative 5 over plus 2, that really doesn't matter because this thing is so big that subtracting 5 and adding 2 essentially does nothing. So let's start first by acknowledging as n approaches infinity, n minus 5 over n to the 4th plus 2 behaves like n over n to the 4th. And so n over n to the 4th is really what? 1 over n cubed. So as we get out to n approaches infinity, as this thing becomes extremely large, the minus 5 and plus 2 really don't matter. And so you'd have n over n to the 4th, which is really like 1 over n cubed. The next thing I would note, okay, 0 is always going to be less than or equal to n minus 5 over n to the 4th plus 2 at any certain point once you get very large. I'm also going to note that that is going to be less than n over n to the 4th. Right? If you're subtracting from the numerator and adding to the denominator, you're definitely making this thing smaller. So n minus 5 over n to the 4th plus 2 is definitely less than n over n to the 4th, which equals 1 over n cubed. Now we know 1 over n cubed, because of the p series, must converge. So since 1 over n cubed converges. Now I should really note that that's the series 1 over n cubed. Then we know the series as n equals 1 to infinity n minus 5 over n to the 4th plus 2 converges also. Alright, we're going to use that same idea, but now we're going to look at an example where we can actually use comparison to show that something diverges. So if we're looking at this example, as n approaches infinity, 8 over n cubed plus 2 divided by 2n to the fourth minus 1 behaves like, so as you get out super large, that plus 2 and minus 1 are essentially irrelevant, behaves like 8n cubed over 2n to the fourth. And if we simplified that, you would have 4 over n. Now, the next comparison that we want to make is we want to think, okay, how are all these things related? Well, 0 is always less than or equal to 4 over n. As n gets very large, obviously this has to be a positive number, which equals this 8n cubed over 2n to the fourth. That is actually going to be less than, because if you think about it, if we're adding 2 to the numerator and subtracting 1 from the denominator, you're making the numerator bigger and the denominator smaller. So that 8 over n cubed 2n to the fourth has to be less than 8n cubed plus 2 over 2n to the fourth minus 1. So the smaller thing, 4 over n, because that's a p series where n equals 1, 4 over n diverges. So since the series from n equals 1 to infinity of 4 over n diverges, because it's a p series with with p greater than 1, and it's less than the thing we're considering, we know the series from n equals 1 to infinity of 8n cubed plus 2 over 2n to the fourth minus 1 diverges also. Alright, so moving on to our next test. This is a more mathematical way of approaching series. So for a series, a sub n, suppose the sequence of the ratios. So if we look at the ratios, a sub n plus 1, so if we take the next term and we divide it by the absolute value of the previous term, a sub n, and it has a limit. The limit as n approaches infinity. So we're going to take this limit and we're going to look at what happens to L. If L is less than 1, then the series converges. If L is greater than 1 or we get infinity, the series diverges. And if L equals exactly 1, then this test shows nothing and we're going to have to move on to something else. So this is called the ratio test. We're going to essentially compute this number and see what the value is, and then come back and look at these three things. So in this example, we're going to look at something that involves a factorial. A factorial is actually going to come back up in sections 10.1 and 10.2. So I just want to recall what a factorial is. So let's say you had 6 factorial. 6 factorial is really telling you to do 6 times 5 times 4 times 3 times 2 times 1. So that's what we mean by factorial. Okay, so how are we going to use that to help us with this unique series from 1 to infinity of 1 over n factorial? Well, we need to use, if we're going to use this specific test, this ratio test, we need to look at the limit as n approaches infinity of 1 over, now this is going to be interesting, it was a to the n plus 1, so the next term. So we're really going to look at n plus 1 factorial on the top, divided by the absolute value of 1 over n factorial. So we need to think about what's happening here. This is really the limit as n approaches infinity. And since it's absolute value, we know this thing is positive. This top number, n plus 1 factorial, what does that really mean to us? Well, that means we need to take n plus 1, and we're going to multiply it decreasing by n, and then we would multiply it by n minus 1, n minus 2, and on and on and on. On the bottom, we'd have 1 over n factorial. N factorial is telling us to do n times n minus 1 times n minus 2, and so on, so on, so on. Essentially what I'm looking at is this pattern, right? If you called 6n, you would do 6 times n minus 1 would be 5, times n minus 2 would be 4, and so on. So I'm recognizing that pattern. That's how I came up with these terms on the top and bottom. So this is going to be the limit as n approaches infinity. If you thought about how would we multiply by those things? You would have 1 over this n plus 1 times n minus 1, n minus 2, and so on, times, if you multiplied by that reciprocal, n minus 1, n minus 2, and on and on and on, over 1. If you look at that multiplication, the n over n minus 1, n minus 2, and on, those things cancel. And so what we have is the limit as n approaches infinity of 1 over n plus 1. Plugging in infinity, 1 over infinity is 0. So what that shows is that L equals 0, which is indeed less than 1. Since L is 0, which is less than 1, we know that this series from n equals 1 to infinity of 1 over n factorial converges. So this next test isn't just some straightforward calculation that you could do. Instead, you have to use a little bit of creativity, and you're going to need to think about a series that you know converges or diverges, and then do some math with it. So suppose a sub n and b sub n are both greater than 0, so they're both positive for all n. If you do the limit as n approaches infinity of a sub n over b sub n equals c, and c is greater than 0, then both of these series converge or diverge. So we're going to pick some additional series that we know converges or diverges, and we're going to do this calculation and see if we get a c greater than 0. So let's look at this one. We want to determine if this series converges or diverges. And this looks like something you may want to use that comparison test that we did in those first few examples. So if you think about it, as n approaches infinity, n squared minus 5 over n cubed plus n plus 2 behaves like n squared over n cubed, which equals 1 over n. And we know 1 over n diverges. So ideally, if 1 over n diverges, then what we would like to have happen is we would like this thing to be greater than the 1 over n, because if the smaller thing diverges, then the larger thing must diverge. However, n squared minus 5 over n cubed plus n plus 2 would actually be less than 1 over n, because you're subtracting from the numerator and adding to the denominator. So comparison test is not going to work here. So let's erase this. This is not useful right now. So what we're going to do now is we're going to use this limit comparison test, and I'm still going to use 1 over n. So I'm going to let my a sub n series be my n squared minus 5 over n cubed plus n plus 2. And I'm going to let my b sub n be 1 over n, which I know is will form a series that diverges. So what we're going to do now is compute the limit as n approaches infinity of the a sub n series and I'm going to divide it by the b sub n series. So that's the limit as n approaches infinity of n squared minus 5 over n cubed plus n plus 2 times n over 1, which equals the limit as n approaches infinity of n cubed minus 5n over n cubed plus n plus 2. And similarly, as n approaches infinity, this behaves like n cubed over n cubed, which equals 1. So the limit as n approaches infinity of n cubed minus 5n over n cubed plus n plus 2 is 1. So we have a c that equals 1, which is greater than 0. That means both of these series either converge or diverge. We know 1 over n diverges. Thus, the series from n equals 1 to infinity of n squared minus 5 over n cubed plus n plus 2 must diverge. Alright, now we're going to actually look at a really easy series to do. It's called the alternating series, and an alternating series is simply one where you have negative 1 to the n minus 1, or you could even have negative 1 to the n. All we're looking for is that the signs between each individual term change. If the signs change, an alternating series will converge if the limit as n approaches infinity gives you 0. Okay, so essentially what we're saying is we want to take out the alternating part and only look at what's left. So if I'm looking at this series here, does this series converge? This is an alternating series, negative 1 to the n. That's going to make the signs flip. If I take out that negative 1 to the n, then the a sub n part is really just 1 over 2 to the n. So if I look at the limit as n approaches infinity of 1 over 2 to the n, you really just have 1 over infinity, which equals 0. And so by this rule, the alternating series will converge. So it's really simple. If you have an alternating series, take out the alternating part, look at what's left, do the limit as n approaches infinity of what's left, and if you get 0, the series will converge. Let's talk about another important aspect then. What it means for something to do what we call absolute convergence. We say a series a sub n is absolutely convergent if the absolute value of it converges as well. It is conditionally convergent if the series a sub n converges, but the series of the absolute value does not. So let's say we want to determine if this alternating series converges from 1 to infinity, negative 1 to the n minus 1 over n. So let's just start by looking at whether it converges or not. This is an alternating series. The a sub n part, if I took out the alternating part, I would just have 1 over n. And if I look at the limit as n approaches infinity of 1 over n, it gives me 0. So the series converges. However, if I want absolute convergence, if I was to take the absolute value from n equals 1 to infinity, if I did the absolute value of -1 to the n minus 1 over n, I would have a series without the alternating part. Everything would be positive. So the alternating part would go away, and I would essentially have the series from n equals 1 to infinity of 1 over n. Well, that's a p-series that we know does not converge. This does not converge. Because it's a p-series with p equal to 1, thus the series is conditionally convergent. Meaning it will converge if it has that alternating part, but if you take out that alternating part, it will no longer converge.